fine.
Yeah, I got
it. Good?
Yeah.
Is it recording?
Yes.
Okay, good. Welcome, period. Welcome, period 3. You are taking the comp sci exam tomorrow, so you cannot have class. So you're going to watch it, sophomores at least. So we're recording period 4. Everyone in period 4 say hi. Hi. Maybe we do a quick pan. And then,
I don't know. I actually had to move it. Like, I have no idea how to turn this. Huh?
And we're gonna try to make
class
a little bit fun for you.
You actually just like move this whole thing.
Actually watch video. So we're gonna have fun today. This is actually one of the more important lectures. In fact, the most important day of your life.
This is so bad. How do you even actually turn this thing?
Can't you just twist it?
No, you can't just twist it.
Okay, it's fine. It's fine. Avery's fine. Avery's fine. Avery's fine. Avery's fine.
Yeah, I know.
The most important day of your life is coming up soon. And that is
that would help.
Fundamental Theorem of Calculus Day. So all of the days leading up to Fundamental Theorem of Calculus Day also really, really important. So this is probably like the 6th most important day of your life. Okay, first, something not super important, but still kind of important. There was homework. Good. Things to do today. Breathe in, breathe out. Aww. Okay, good. Let's go over the homework on parametric equations. It was page 725. I think we had a pretty decent lecture on this last class. Some of these problems are a little bit tricky. Let's do, say, like 3 of them. Michaela, which one should we do?
I know.
So the homework was 1, 8, 9, 14, 24, 29, 33, and 39. I propose that we do 14, seems like a good problem. Possibly 24 is actually exactly like the problem that we did in class, and maybe like 39. That should be sufficient, I think, yeah? Okay, good. 14 says, find dy dx and d squared y dx squared and find the slope and concavity if possible at the given value of the parameter. So in number 14 you are given 2 equations, x equals theta minus sine theta and y equals 1 minus cosine theta. And you had to find the slope of the tangent line to the curve and also the concavity of the curve at theta equals pi. So we're doing this all at theta equals pi. Okay, so let's do it. I want to know what dy dx is. Well, last class we learned that dy dx is just going to be dy d theta over dx d theta. So we can just differentiate these individually. Derivative of 1 minus cosine theta, I guess that's just sine theta, yeah. Over the derivative of this would be 1 minus cosine theta. So there is my formula in terms of theta for dy dx. I think I did that right, yeah? Yep, looking good. Okay, and now I specifically want dy dx at theta equals pi. So I plug pi in for theta, and I guess it gets 0. It's kind of boring. So there's going to be a horizontal tangent there at theta equals pi. Okay, then I want d squared y dx squared. Okay, so this is asking for, the way I think of it is, it's the rate of change with respect to x of the slope of the tangent line to the parametric curve. So it's the derivative with respect to x of dy dx. And for reasons that we talked about last class, in order to calculate the derivative with respect to a variable, or taking the derivative of dy dx with respect to x, this is going to be the derivative with respect to theta of dy dx over dx d theta. Everyone cool with that? Okay. So what is dy dx? Well, we did that in the last in the first part. So what I need to do on the top is I need to differentiate this with respect to theta, and on the bottom dx d theta. I guess I already did. That's just 1 minus cosine theta. All right. So I'll just use the quotient rule. I guess seems simplest. So derivative of the top is cosine times the bottom 1 minus cosine. The top is 1 minus the top times the derivative of the bottom and the derivative of 1 minus cosine theta is just another sine theta, yeah. All over, bottom squared, and then the whole thing is over dx d, or yeah, dx d theta. Okay, so when I do this all out, do I get something kind of nice? I feel like I do. Because I get cosine minus cosine squared minus sine squared, that whole thing just becomes minus 1, right? So we get cosine minus 1 on the top, cosine theta minus 1 on the top, I'm skipping some steps, over 1 minus cosine theta cubed. And then even that will simplify because I can cancel one of the 1 minus cosine thetas after pulling out a negative. Alright, so my answer is that this is negative 1 over 1 minus cosine theta squared. Is that what you guys got?
Michael.
No? Someone back me up. Prem got that, good. Alright, so having figured out this formula in general for d squared y dx squared, I can now figure out what is the concavity, what d squared y. What is the concavity specifically at theta equals pi? When I plug in pi for cosine, that's negative 1. So 1 minus negative 1 is 2. So I think my final answer is negative 1/4. Maybe that's what you got?
Yeah.
Raise your hand if you got that.
What was the
Oh, like 6 people. What was the problem?
what was d squared y over dx squared?
Negative 1 over 1 minus cosine theta squared.
Yeah.
Yeah? And then you got negative 1/4?
Yeah.
Okay, cool. Okay, good. Questions on that? Okay, good. Let's do like 2 more. 24 was almost exactly like what we did in class. So I think if I just signed this problem to you cold, I don't know if you would have been able to figure it out, but x is t cubed minus 6t, y is t squared. And the question is, find the equations of the tangent lines at the point where the curve crosses itself. So if you try to do some analysis of this, t cubed minus 6t, well then that's just t squared minus 6. Did you guys see this as being almost the exact same thing? Like it was literally like one number change from the problem we did in class. So if you factor a t out of the x equals equation, then you get x equals t minus root 6, t plus root 6. And that enables you to make a sign chart. The sign chart for x is that it's just always positive, or y rather. But the sign chart for x is that it is going to be cubic-y with respect to t, or actually just cubic. So it's going to change signs at 0, negative root 6, and root 6. And it's going to go negative, positive, negative, positive. All right, all of that is just for you to sort of figure out that this curve, what it's going to look like, it's sort of going to be sideways Jesus fish now, I think, right? Like upside down, diving. Because now the y coordinate's always going to be positive, but it's the x coordinate which is going to change over time. And in particular, t equals 0 seems like worth talking about. T equals root 6 seems like worth talking about. And when I plug in root 6, I get y is 6 and x is 0. So that means that I'm going to have this point 0, comma 6, that I'm going to be here at both t equals root 6 and also t equals negative root 6. And because this curve starts at negative infinity, comma infinity, way up here somewhere, that means it comes through here, and then it's going to do basically like this. I kind of just know this, but you could do more math to figure out that this is indeed the shape. The book asks you to find the slope of the tangent line, or just as for the equations of the tangent line to the curve at the place where the function crosses itself. So you had to first figure out that this curve does cross itself. It crosses itself at the point 0, 6 at time t equals root 6 and t equals negative root 6. Cool? Okay, so now you just do it. What is the slope of the tangent line to this parametric curve? Well, in general, it's going to be dy dt over dx dt. And then we can just kind of like do them, right? This is 2t, and this is 3t squared minus 6. Yeah. So what is dy dx at t equals root 6? At t equals root 6, I just plug in root 6, I get 2 root 6 over 18 by 12, yeah. So that's going to be root 6 over 6. And the other one, dy dx at t equals negative root 6, I think that's going to end up being negative 2 root 6 over still 12, so negative root 6 over 6. So that tells me what these slopes are, and then I can write the equations. One of the equations, this one is, well, basically it's just going to be y minus 6 equals plus or minus root 6 over 6x. Those are the two equations. How are you feeling about this? Yo.
Oh, I couldn't find where the graph crossed itself. I just didn't know what it looked like.
You just didn't think to do that.
Just graph it.
Yeah, I didn't really graph it, although I guess I kind of did. I guess I just thought about it. Yeah, this could be a hard problem, right? Like, where does the curve cross itself? Well, I guess if the curve crosses itself, then the way to think about it is it has to be in the same place at 2 different times. Okay, right? So where is this curve ever going to be in the same place at 2 different times? Well, for starters, we can look at the y-coordinate, and we can say, since y is t squared, then the only time I'm at the same height is if I'm at opposite t values. Okay? This could have been your thought process. So if this curve is going to cross itself, apparently it does according to the book, then it's got to be in the same place at 2 different times. Well, those 2 different times must be opposites of each other, right? And then if they're opposites of each other, if you think about this t cubed minus 6t function, I don't know, did anyone actually do this? Plug in t and negative t and it works out? Is that what you did?
I took some t sub a and t sub b and then did a bunch of stuff and you get plus or minus root 6.
Yeah, it's if you didn't think to graph it, you could do it heat set. So, but you first did the thing I was just saying right now, right? So a serious approach to this problem, besides just thinking about it and kind of guessing and checking, which is sort of what I did. What Elijah says is, he kind of just said what I said, which is that we're looking for 2 different t values with the same x and y coordinates. Well, the only place with the same y coordinate is they have to be opposites of each other. So I'm looking for some value t such that the x coordinate gives me the same for it and its opposite. So when is t cubed minus 6t going to be the same as negative t cubed minus 6 times negative t? Does that make sense? I'm looking for the t value at which the x coordinate is the same for it and its opposite. And then that turns into t cubed minus 6t equals negative t cubed plus 6t. And then you just kind of solve this equation basically. It just sort of works out, yeah. So we get 2t cubed minus 12t. So that's t cubed minus 6t all over again. And so the answer is that this is going to happen by solving this equation. That tells me that, so that's a more kind of principled way to do it. Okay, good. Should we do one more problem or do we feel good? Should we do one more? Let's just do one more. 39 says, determine the intervals on which the curve is concave downward or concave upward. So here the curve is x equals 2t plus ln t, and y is 2t minus ln t. So now we just do it, I guess, right? First I can find the slope of the tangent lines of the curve. So that's dy dt over dx dt. And that's going to be 2 minus 1 over t over 2 plus 1 over t. I think I want to simplify that, right? Because that's going to be, if I make a common denominator on the top and the bottom, the t's are going to cancel. So this is 2t minus 1 over 2t plus 1. Is everyone okay with that? Okay, so that's the slope of the tangent lines of the curve. I want to know about the rate of change of the slope of that tangent line. Elijah, can you close the blinds? Blair. So I want to know d squared y dx squared, that's the rate of change, both of them, and actually like do it, of the rate of change of this. So now that's going to be the derivative with respect to t of 2t minus 1 over 2t plus 1 over dx dt. And now I guess I just have to do a bunch of work that I'm not exactly in the mood for, but let's do it. So derivative of the top times the bottom minus the top times the derivative of the bottom all over bottom squared all over dx dt, which is 2 plus 1 over t. Now, is this what you guys did? Now I just have to do algebra. I don't know why I'm whining about this so much. Okay, let's do it. 4t plus 2 minus 4t plus 2. Yeah, all over. I have a 2t plus 1 squared, but then I also have down here, that might as well be like 2t plus 1 like over t. So now I guess I'm going to do some advanced middle school flippy, and this becomes 4t over 2t plus 1 cubed. Someone back me up on that?
Yeah.
Okay, good. So that expression represents, is a formula which will tell me for a given t value whether the slope is getting bigger or smaller, slope of the tangent line to the curve. All right, and now they want to know when is it concave up or concave down, so that requires making a sign chart for this expression. So the numerator is going to change signs at 0, and the denominator is going to change sign whenever 2t plus 1 changes sign, which is at t equals -1/2. So this is going to be quadratic-y, a lot of math going on here, but I get this. So claim it's going to be, this curve is going to be concave up on the t interval from -∞ to 1/2, from 0 to infinity, and it's going to be concave down in the t interval from -1/2 to 0. The only twist is that the domain of this curve is only from 0 to infinity, because that's how ln works. So the actual answer to this problem is, this is just garbage, and this curve is going to be concave up everywhere. Aww. Off camera, I just made that shot. Period 3. Okay, good. That was our homework on parametric equations. Let's do a couple quick shout-outs. Who wants to go first? Ryan.
Okay. So, hey Anna, I wasn't gonna make you a shout out, but I thought that would be meme, so.
2 minutes there. Good. Anyone have like, let's do like 2 or 3 more? Divya. Wait, fast.
Shout out to Emma, you're really tall.
Okay, good. Just do your other one while you're here.
And Reethi, I admire your youth.
That's hilarious. Okay, let's do like 2 or 3 more really quick. Who else wants to go? Okay, Herval.
Oh my god, Elaine, stop. I am going to throw this at you.
Okay, I don't understand.
You don't get this.
Inside joke. Okay, good. Anyone else want to go? Otherwise, we can do it later. Michaela?
No.
Oh, she's making things for camera. Michaela, just go.
Okay. Hannah, just keep swimming.
Okay, good. So, can you take out the second half of the homework was on, second half of the homework was on area. I thought we could do like 1 or 2 problems from that, yeah? Yeah, I'm gonna go over there to that board.
Great. No, that's what I told me.
And maybe can we just do the last problem and then just that kind of covers like everything. If you can do the last problem, you can do anything. That was like number 55.
Not a good angle.
You're not a good angle.
What kind of success rate did we get at all of this?
Stop focusing on Robert's
Low?
face.
I got an answer.
What was your answer?
A6 thirds.
Oh yeah, that's wrong. Yep, you got 2/3?
No, no.
Good, let me wind up, can you raise the board? Okay, so 55 gave you the following curve. The curve is y equals x squared minus x cubed, and they wanted it on the interval from -1 to 1. Okay, let's spend some time on this. This is exactly like what we did in class, just at the end of last class. But you have to kind of get it right. And there's like so much going on. I think all things considered, this is probably one of the hardest things that math that you've ever been asked to do here in the Magnet program. Because you have to really think about what's going on. Okay, so let's take it slow. First of all, let's get a really good graph of this going. So for that, I will try to graph this. I can factor out an x squared, so that's 1 minus x, and I'll also factor out a negative, so that's negative x squared x minus 1. Okay, that means that I know what this curve looks like. It is going to be, let's see, at -1, well there's going to be like a double root at 0. It's a cubic with the double root at 0 and also a root at 1. And then additionally, because of the negative, the end behavior is going to be flipped. So it's going to be like this, right? So it's going to come down, kiss the x-axis at 0, back up a little bit, and then down to 1. Okay, let's get some points. So that means there will be a root here also. All right, where am I at -1? If I plug in -1 here, I'm going to get 1 minus, I'm going to get 2, right? Okay. So, step 1 is to make a really neat, high-quality picture of the situation. And I claim some crap like that is pretty good. Is that okay? Alright, so now what I want is to find the area of the curve between -1 and 1. Is there a green over there? Michael, do you have green on your desk? Oh, there's green behind you. Alright, so.
Dell wouldn't know.
Alright, so the area that I'm looking for, I'll just like very lightly shade it. The area that I'm looking for is this green business right here. Okay, and I want to know exactly the area. And in order to find the exact area, I'm going to first figure out what the area is with n rectangles, and then let the number of rectangles go to infinity. Okay. And I get the choice whether I want to use LRM or RM. Which one do you want to use?
RM.
RM, because LRM sucks. That's what we learned last class. So if we're going to use, one thing is that we're going to use RM. The next thing is that we're going to use how many rectangles? N rectangles. And therefore, if I'm going to use n rectangles, what is delta x, the width of each rectangle? Yeah, the total width of the interval is 2. So if the total width of the interval is 2, delta x is going to be 2 over n. Okay, and now I'm going to start drawing in these rectangles. So here is a rectangle. Here is another rectangle, here's another one, and now I think you can't skip this process where you carefully sort of think about what are these coordinates. So let's take this first point right here. This is the top right-hand corner of the first rectangle. What are the x coordinates of that point? Yeah, what is that? Well, I started at -1, and then I just moved over very slightly to the right. How much did I move over? Moved over the width of one rectangle, and the width of one rectangle is 2 divided by n, because the total width is 2, and there are n rectangles. Is everyone cool with this? Okay, raise your hand if you did the whole thing and you got the right answer, just so I know how many people I'm talking to. All right, so like about 6 of you got it wrong. So I'd like to know where the process is going wrong. So I'm going to just keep asking for feedback. Okay, so over here we get -1 plus, what is that? How much did I move over? 2 over n. So, and I'm even going to write it as 1 times 2 over n, comma, f of that. Okay, cool. All right, now let's take the next y coordinate, or the next rectangle, I guess, that top right-hand corner, what is the x coordinate of that point? Well, now I started at -1. Now I've scooted over 2 rectangles width amount, right? So this is going to be -1 plus 2 times 2 over n, comma f of that. Follow? Okay, and then this point is going to be -1 plus, and now I've moved over 3 rectangle widths. So that's going to be 3 times 2 over n, comma f of that. And you just sort of continue this process until, let's draw the nth rectangle. In this case, the nth rectangle is going to be a little bit weird because it's going to have no height, right? Maybe I'll draw the n minus first rectangle as well. But that's like the n minus first rectangle. The nth rectangle is just going to be flat, but that's okay. So let's go all the way to the nth rectangle. According to our pattern, what should that x coordinate be? Well, I started at -1. How many rectangles did I move over? N. So I'm going to multiply by 2 over n times. And then a check on your logic to make sure that you fully understand what's going on. What is -1 plus n times 2 over n? That just is 1, right? Because n times 2 over n is 2, so it's all making sense. Right, so after you've spent, I think you have to spend, especially the first 3 or 4 times you do this, a lot of time really processing this diagram. But having done that, now we can start to add up all these rectangles. So, alright, what is the area? The area is going to be, and again, I usually skip this step, but if it helps you, let's do it. What's the area of the, let's start calling on to people. Yes?
Wait, I have a question about okay, so like from 0 to like the top of that curve, does it not matter that you're going to be like overestimating instead of underestimating?
Okay, right. Good question. So you're worried about the overestimation, underestimation thing. In fact, maybe this is a good moment to talk about this. Can you flip the camera over here? Side conversation. First problem we did, in the area packet, was a what shape was it? Was it a regular parabola or upside down parabola? The first one was upside down. Yeah. So it looked kind of like this, right? And we did that twice, right? We did it first. We did it as an overestimate, and then we did it as first I said do lower, and then we realized that we needed to use RRAM, and then we did over, and we realized that we had to use LRAM. So what determines? Yeah, not the greatest picture. And then on the second page, we had a different. Now it was a different kind of thing, or page. I guess it was like page 2 and 3 or whatever. Then we were going from 1 to 4, and now things are changed, right? Now, if I use, let's let this be the RRAM column, and let this be the LRAM column. Now what happens? Well, now if I draw rectangles on the right, what's happening? Yeah, it's going to be an overestimate. And now if I draw rectangles on the left, it's going to be an underestimate. So I think I was running out of time, so I didn't quite ask you to generalize this, but what is the key property of the curve which is determining whether we get an overestimate or an underestimate based on the various methods? Okay, I had about 9 people say concavity simultaneously.
Are they all wrong?
I don't know. That would be exciting, right? Yeah. That would be a learning opportunity. Michaela, why concavity?
Teaching moment. I think concavity because for the first graph it's like concave down.
Yeah.
But so like RRAM, like it's an underestimate, but LRAM is like an overestimate. But like for when it's concave up, like it flips. Like RRAM is an overestimate. Well,
No, but
Still concave down, yeah?
boom roast.
Yeah, boom roast. Exactly.
Okay, well.
Wait, is that what Suna just did? Picture worth 1,000 words here. I continued. What? Okay, I continued drawing our rectangles over here, and now it turns out that concavity is not the issue, right?
Yeah.
Okay, so it's interesting. I also I think the first time I taught this, my first year, I was like, oh yeah, it's concavity, right? And then some smart guy was like, no. And I was like, oh crap, I'm wrong. Yeah, it feels like that should be right, but it's not. In fact, it's something simpler. What does determine it? Yeah, just whether the curve is increasing or decreasing. And maybe the best way to see that is just to draw a curve with no concavity. So I guess I need 4 pictures here. Let's see. I'll let this be the on this column I will take a look at LRAM, and in this column I'll take a look at RRAM. Do I need? Yeah, I guess I do. So let's make a curve which is increasing, like a simple one, just like a line. And here I can make a curve which is decreasing. And if I want to find the area under the curve, well, if I'm using LRAM, then every time on each subinterval, I'm using the left-hand endpoint. But if you think about it, and this is getting like deep here, right? If you think about what's happening is, I'm using the left-hand endpoint, but that's going to consistently be an underestimate because the curve is increasing, right? Since it's increasing, on a rectangle by rectangle basis, I will be estimating the function at the spot when it is the smallest that it is going to be over that subinterval, right? Whereas if I use RRAM, now by using the right-hand endpoint of an increasing function, I'm estimating the curve using the value where it is always going to be biggest. Because on any subinterval, the right-hand endpoint is going to have the largest y value. You guys like feeling this? You should let these rectangles into your heart. Down here, with a decreasing function, it is just the reverse. Now, a decreasing function is just getting worse and worse over all the time. And in particular, over any subinterval, it's getting smaller and smaller. So when I use the left-hand endpoint, I'm getting an overestimate because this is the biggest it's going to be. And when I am doing RRAM, I am, bless you, I'm getting an underestimate because I am using the right-hand endpoint as an estimation, but it's always going to be the smallest at the right. Okay, good. Neither of these directly address Jillian's question, because this function, what can you say about this function? Yeah, it's not monotonic, it's decreasing, then it's increasing, then it's decreasing. Okay, so if I was really, so RRAM and LRAM are not necessarily like methods to find where a lower estimate or an upper estimate, right? Here, do you guys see